Libraries, so things like that I already mentioned, things like CUDA-X, which is a library that provides deep learning primitives for GPU acceleration. If you want to develop yourself, so if you're interested in developing some of these frameworks, or you want to develop your own frameworks or your own application, the next easiest path is to use, as I mentioned, libraries. Instead of, for example, let's say you have an application that is using fast Fourier transform or basic linear algebra operation. You're just replacing the calls to your traditional CPU library to the calls with some calls that are calling the GPU library. The next easiest step is using directives oriented programming languages. And again, I'm going to go a little bit more technical. I'm not sure how many of you heard about OpenMP. We have something very similar called OpenACC. OpenACC allows you to do GPU programming by just putting a couple of directives in your code, and the compiler does all the heavy lifting for you. It does the code transformation based on those information, and it will generate the GPU code that runs on the GPU without you actually writing CUDA code. So very easy to transform your code, especially if you already have existing code. And last but not least is actually starting to program in CUDA. And once again, the features that you have in the software go hand in hand with what you have in the hardware architecture. And one of the feature that a lot of people, especially if you've started maybe earlier using CUDA, you might not know about this. It's called unified memory. Unified memory allows you to basically address any GPU from any GPU in a multi-GPU system. So in this case, for example, we are showing a 16 GPU system. Right now we have an 8 GPU system, but we already have the next generation that we launched last year, in which you have 16 GPUs in one single server, and they're all interconnected with a specific, here, no, I don't have it. Anyway, this is how it looks like. But going back, all these GPUs, they are interconnected inside of the system using something called NVSwitch. So NVSwitch allows to interconnect all the GPUs at maximum speed. And then the features in the software, in the CUDA programming language, allows you to access any GPU memory from any GPU memory. So it allows to have a unified view of the entire memory space on the GPUs. And you get a lot of performance. So this is comparing, if you look at all the green lines, are actually two systems, two DGX1 systems, so the one that you have right now. So 2 times 8, you have 16 GPUs. We are comparing with the green line. The green line is a DGX2 with NVSwitch. It has 16 GPUs connected with the NVSwitch. In theory, it's the same number of GPUs. So 16 GPUs here, 16 GPUs here. But because of the hardware and the software technology, you can see that actually the performance sometimes it's double, if not more, for the exact same number of GPUs. It's the hardware plus the software that makes this possible. So all in all, when we're talking about the CUDA libraries, I'm not going to go into a dedicated CUDA training. We could do that. As I said, I've been doing CUDA programming for the past 10 years, so we can have a separate discussion if you're interested, or we can organize another workshop specifically only for CUDA. All the libraries that I mentioned, they're under the umbrella of CUDA-X, and if you go to the NVIDIA website, you can find both CUDA-X HPC, which are HPC libraries, and then you have the CUDA-X AI. As I said, there are more than 40 libraries right now, but I'm just going to show you a couple of them. One of them is CUFFT. The CUFFT again, quite fast Fourier transforms, which are again very used in all sorts of application in traditional simulations. Just to show you a couple of numbers, this is just the improvement, and once again I want to stress that the performance that you've seen, the increase in performance that you've seen from one generation to another generation of GPU, it's not just the architecture itself, it's the software too. And here if you look, it's a comparison of two versions of the same CUFFT library. So this is the latest version, CUFFT version 10, and the gray one is CUFFT 9.2, so it's one generation before. And as you can see, in this case in particular, the more GPUs you add, the more performance you get into the new library. This is because, once again, we work a lot in improving the way that the communication happens in the library and all the underlying things in the library itself. Next example, BLAST. Again, if you've been doing traditional simulation, BLAST might be familiar. It's basic linear algebra. You might use that. There are other libraries that already implement BLAST on the CPU, so it's very used library. We implemented the GPU version, and once again for different size of problems, and for in this case we are actually comparing the current version of GPU with the previous version of GPU. Once again, as you increase the size of the data that is being computed, you get a big increase in performance. CU Solver, yet another library. If you're doing things like elastic factorization, QR factorization, again, these are more traditional HPC type of applications. We do provide this type of libraries. Again, very good speed up. This is something in between HPC and deep learning. Deep learning is using a lot of, or deep learning is applied a lot in image recognition, object tracking. And one of the basic operations that you have to do in deep learning in image recognition or object tracking is to work with images, obviously, as the name says. And you need to have a very fast library that is decoding those images, whether those images are coming from your smartphone, from a camera, from a video feed, so a frame in a video, you need to decode those images. So we created this NVIDIA APAC, which is a very fast decoding library for JPEG images. So this was a very quick oversight of a couple of libraries that are most commonly used. I think they are the top 4 or 5 applications that in terms of downloads and usage inside of our NVIDIA developer program. We're also trying to make everything easy for the developer. Whether you're using CUDA or whether you're using libraries, we want to make all this easy from a programmer perspective. So that's why we put in place an entire development ecosystem. If you've been doing development on a CPU, you probably know that it's very difficult to get things right from the beginning. You cannot just start writing code and then you run it on the CPU and it just works. So you need this kind of tools, things like debuggers, profilers, that allow you to make sure that the application, when you run into a problem, when you're developing your code, you get some assistance. So we have a bunch of applications that are available under the umbrella of Nsight family. So the Nsight family is basically a suite of programs that are providing capabilities for developers. So Nsight system is providing profiling both on the CPU and the GPU. And again, I did mention this at the beginning. Don't imagine that the entire workload or your entire application will run on the GPU. The GPU still remains an accelerator. It still requires a CPU that, in the best case, is only orchestrating the data transfer between the CPU and the GPU. But you still have code that runs on the CPU. No matter if your application is meant to run on the GPU, you will still have a very small portion that runs on the CPU. So that's why it's very important to have a tool like this that allows you to profile and debug what is happening both on the CPU and on the GPU side at the same time. Then we have Insight Compute. So Insight Compute allows you to look deeply into the execution on the GPU itself. So you can get very low-level kernel profiling. This is especially useful either when you're having issues with your application or when you're running into issues and you don't get the expected result. As I said, GPU programming and parallel programming in general, even on the CPU, it's not always trivial. So you need this kind of features, and we do provide them. I'm probably going to skip all this. I'm not going to go into all the details. I'm just going to refer you to one single website, developer.nvidia.com. If you're a developer or if you're using any of our tools, I highly encourage you to subscribe to the and become a registered NVIDIA developer. First of all the tools, they don't cost anything. So all the software from NVIDIA comes for free. But if you're a registered developer, you get two things. First of all, you get support. We have very good forums where a lot of our engineers, a lot of my colleagues, and including myself, we are active there on the forum. So if you run into a problem as a registered developer, you have access to all these things to get help, because you're not alone in your quest. Secondly, as soon as we release a new version, and sometime you can even get an early access to different tools before anyone else, and you get so basically you get access firsthand to the best goodies. So it's free to register. Again, no fees involved. Just sign in with your email address, and you get a developer account. And once you're on the developer.nvidia.com webpage, you have links from there to all the development platform that we make available. So from there, you can get the CUDA toolkit, you can get the libraries, you can get the different tools that I'm presenting here. So that's why I'm going to skip them right now. The next part that I mentioned that allows you to have a very easy entry point is OpenACC. OpenACC, as I mentioned, it's a programming model where instead of writing codes or instead of writing explicit CUDA code, you just need to put a directive. That directive, it looks something like this. So again, I don't want to become very technical, but if you know a little bit of C, this might look very familiar. And this thing here in green, hash pragma ACC kernels, it's the only thing, for example, that you need to put in your code to instruct the compiler to, out of this portion of code, out of this block, to generate a GPU code. So this one single line like this can allow you to run on the GPU. So very, very easy to parallelize your code without knowing any CUDA programming. And it's also very easy to start. Obviously, you need a compiler that understands this. Again, if you've done some development, you probably know that you have different tools. On Linux, you have things like GCC, Intel compilers. On Windows, you have Visual Studio. So you have to have a compiler that understands this type of comments into the code, because otherwise, if the compiler doesn't understand this type of pragmas, it will just ignore it. That's the beauty of it. You can put those comments in your code. If you compile the code with a compiler that doesn't understand them, it will just run as normal. It will run on the CPU. But if you use a compiler that understands these comments here, it will do the magic. So that's when the magic happens. And the magic tool is actually called PGI. So the PGI compiler allows you to compile OpenACC code. There are multiple versions. You have the community edition, which everyone can download. So once again, if you're registered as a developer, you can get a license that basically can be renewed every year. So you can get it renewed indefinitely. Obviously, if you want to go more on the support side or more towards the industry side, we do have professional and enterprise versions which provide additional support. But just to get started, the BGI community is very good for you. Should we take a 5 minutes break? Because I think we're a bit over the. Okay, so let's take a 5 minutes break. Any questions up to now?
No.
Okay.